Uh, Good morning, everyone. I'm glad many of us here, and thanks for everyone who joined early in the morning. My name is Ferenc Fejes. I'm presenting this work on behalf of my colleague Ferenc Orosi. And essentially, this will be about a CNI plugin, a Kubernetes CNI plugin. My research area at Ericsson Research is time-sensitive networking. So it's not the usual data center or hyperscaler AI networks mostly talked about here. These are very specialized networks where robustness and low jitter are the most important thing. Also power efficiency, time sync is required, and they are used at the field or inside automotive and aerospace applications like planes and helicopters. Also, they are used to control plants and industrial machines, welding machines and stuff like that. So just to give a bit of a context for my talk. Also some additional context that, of course, like the main direction of application deployment nowadays is microservices. And this trend is emerged in the industrial applications as well. So people from manufacturing companies come and said they need the same flexibility and observability what anyone used to have in a Kubernetes cluster, but they want to use that on the field with robots and controlling robots and virtual programmable logic applications. However, there are some challenges. And now back to the kernel, some familiar topic. So here's the simplified version of the SKB structure, lots of fields omitted. What's important for us here for the time-sensitive networking is the priority and the timestamp. Because these are the fields used by time-sensitive queuing disciples like MQPrio, time-aware priority, ETF, and also for VLAN priority tagging, the SKB priority used as a primary source to set the priority tag. So these are important fields for us. And the user space application can set these fields for UDP packets or RAW Ethernet RAW packets with these APIs, with setsocopt API. So for example, the SKB timestamp set by the SOTX time control message or ancillary message. This is available since 4.19. And SKB priority can be set by SO priority setsocopt for socket wide. So you define a UDP socket, set it with the setsocopt. This is here since forever, since 0.98, and it's released more than 30 years ago. And you can also set it per packet, but that's a more recent addition to the kernel. And when it comes to network namespaces, which is used heavily to isolate microservices, for microservice network isolation, the two important function here is the dev forward SKB and SKB scrap packet. And the dashed line here represents the boundary of the namespace, two network namespaces. So here's two VETH interface, and here's the network namespace boundary. In the dev forward SKB, again, it's a simplified version, but if there is a network namespace crossing during the forwarding, we call the scrap packet metadata, which removes the metadata from the SKB. Originally, this function introduced for tunneling. So when a packet got tunneling, it's called the SKB scrap packet to remove every metadata which might belong to a header processings before the tunnel. And also, this removes the priority as well. So this is not happening in the scrap packet. For some reason, this is happening here in the dev forward SKB. Just to show you the simplified version of the scrap packet, if there's no namespace crossing, it can leave the mark as is. But if there's namespace crossing, so it can go, the packet going through from one network namespace to the other, it also reset the SKB mark as well. So we cannot get away saving the timestamp or the priority into the SKB mark, because that will be cleared as well. And the timestamps, we have easier job with the timestamps since they are only cleared conditionally. By the way, the SKB mark discussed heavily in 2 days ago at the rich packet metadata talk, so I recommend that. Okay, so in this BPF data path extension for Kubernetes workloads LPC talk, there are in part 2 there was the reason it was presented why we cannot just remove the timestamp in every condition. There are cases when we need this timestamp. So we have easier job with the timestamp, since if the timestamp type is not real time, I guess this is the first in the SKB timestamp type enum. So if it's monotonic or TIE, that indicate the network stack. We want to keep the timestamp no matter what. Okay, just a brief, a quick recap what we know so far. We need timestamp and priority for TSN networking. They cleared by the namespace isolation, unfortunately. If we use different clocks than the clock real time, wall clock, these are preserved. And so in TopRio and ETF QDisk, we can use those, but we still lost the priority. And now let's continue with Kubernetes networking. Kubernetes offload the network configuration for CNI plugins like Calico, Cilium, Flannel, Weave, and similar plugins. These plugins do the heavy lifting. They configure the virtual interfaces, the routing between them, switching between them, firewall rules, and these kinds of stuff. And most of these plugins, not every plugin, because some of them rely on DPDK or other kernel bypass technologies, but most of these plugins, especially what listed here, these plugins using the GNU Linux tools and APIs to build the network, to implement the cluster networking. Okay, and why this is important? It's important because the pods isolated with unique network namespaces from each other and from the host network or the root network namespace or the node network namespace. So if we deploy an application as a microservice in a pod, metadata get removed. So the CNI plugins network, we lost the metadata even before it reaches the CNI plugins network. And when it comes to the physical interface, if the packet leaves the node, we don't have the timestamp and priority anymore. So for time-sensitive application, there are some challenges. There are lots of different CNI plugins. We cannot tell, we can't say to the developers that please use your vendor-tailored API just to preserve scheduling metadata. We have to rely on Linux APIs. And there are no option to keep the metadata, keep the necessary metadata from the isolation process. And here's a small, I will come back to this later in the presentation. So this is not entirely true. Now I'm just talking about VETH. Okay, so we propose a CNI plugin. It's called TSN Proxy, which intend to equip the primary CNI plugin listed before, like Calico, Cilium, and such plugins to the TSN metadata preservation. And we want to do this without the modification of the application, without kernel bypass or custom compiled kernel, of course. So as you might guess, we might use iBPF for this. So our intention is a similar setup where there are the time-sensitive application pods. And there's the cluster network, and all the heavy lifting does by the industry strengths popular CNI plugins with every feature they support. And here's our secondary CNI plugin, which do some fine tunes on the network, what they configured by these plugins in order to preserve the TSN metadatas. So this is a simplified, of course, this is a simplified diagram from the pod initialization process. It's not entirely looking like that, but when the API server or the Kubernetes scheduler instruct the kubelet to schedule a pod on a node, the pod requests the kubelet network. The kubelet request from the CNI interface of Kubernetes a network, which allocate a namespace, and of course there's an IP address allocation, but let's say it allocated the IP address as well, and the CNI instruct the first plugin to please use this network namespace and IP and configure the network. And this primary plugin get back to the CNI with the VETH and some other data. It returns some other data. And then if is there any other plugin in the CNI plugin list that gives the CNI framework give the things returned by the primary plugin to the other plugins and so forth. So you can chain multiple plugins. So now in our TSN proxy, we have the network namespace, the VETH, so we can do whatever we wish with those things. For example, attaching custom eBPF proxy into that one. And we do that. So it's right now, I would like to call it something like a poor man's packet traits, or a very simplified version and not industry strengths packet traits, because we attach a BPF program which is a TC egress BPF program lies on the ETH0 VETH of the pod. And when the pod application sends some data, we check the SKB timestamp and SKB priority and put into a pre-allocated hash map. And here's the address of the SKB and the metadatas. And then it continues the path in the CNI network, the cluster network. It comes to a bridge, may be forwarded, it maybe reach a virtual routing and forwarding tunnel or tunneled elsewhere, a VXLAN tunnel, GNV tunnel, and then reaches the NIC or not, if it's robbed by some rules or egress policy. But what we can do here is we also hook into the TC egress on this NIC, and we can restore the metadata from the hash map based on the address of the SKB. But of course, the address of the SKB can change as it traverses the network stack. Therefore, we introduce some maintenance, and these are, we hook into the SKB clone, SKB copy, PSKB clone, and I think that's all what we use right now. And of course, we do a garbage collection, since if a packet dropped before it reaches the physical NIC, it would remain forever in the hash map, and we can't let the hash map growing indefinitely. So here's just a brief example what might packet tracking looks like. It's a very simplified packet tracking. So here's the original SKB. It has prio 1 and tstamp 1. It has the address. It has an address. And of course, first it comes to the SKB scrub, so it removes everything from it. And then we call the network stack call SKB clone if it's going through a bridge or other places. And of course, this allocated as a different address without the metadatas. But since we are with the FactSet SKB clone, we see the original address and the newly allocated address, so we can create a new entry in the BPF hash map with these metadatas. And this tracking was inspired by the Peru tool from Cilium. They use, I think, exactly such kind of packet tracking. And we also do garbage collection. Our CNI plugin cannot have a user space counterpart. Everything is just in-kernel eBPF codes, eBPF programs, because there are not much state to maintain. So a bash script plus a few BPF programs. And what we do, periodically going through the BPF hash map, and since we have timestamps, we can check whether the timestamp is old enough, like more than 5 seconds or so. So that would be unrealistically high delay, so we can remove those from the BPF hash map. We implemented this with BPF timer. And so the loading of the garbage collection is like, we can load it as, or the CNI plugin load that program once. And the bash script, the CNI plugin's bash script also initialize the timer. And that happening once. And then, so we use the BPF program. It's a very good feature of BPF tool. It's used for testing BPF programs with specified data. Right now, we didn't use this data. We just want to execute a kernel BPF function one time. And the callback, there's a callback, the BPF timer callback will rearm itself indefinitely. So every 5 or 2 seconds, it will recall itself indefinitely. So no user space part needed for garbage collection. And I would like to show you a simple scenario where we have two talker pod. That's how the TSN networks work. They're usually a talkers and listeners, no bidirectional streams. So it's unlike regular communication where there's a session and the two peers, they are communicating with each other. Here we have only talkers and listeners, unidirectional streams. It has no concept of bidirectional streams. If you want bidirectional communication or some sort of feedback, you can treat them as two separate unidirectional streams. They have different config. Okay, so one pod sending with priority 1, one pod sending with priority 2. Of course, there's the CNI network going to the NIC. Then going through the time-sensitive network, there are bridges with enforced time slots for priority 1 and priority 2. Then they reach the listener 1 or listener 2, depending on their priority. Very simple. And on the NIC 0, we define the time-sensitive QDisk time-ever priority. If you're familiar with it, it looks like this. It's basically, you can define traffic classes and open or close a gate for such traffic class. So if a gate closed and packet classified for the closed gate's traffic class, it will remain in a queue. And when the gate opens, it will send it out as a burst. And the gates are defined with bit mask. So these are bit mask values. Think about like this. Think about these as a bit mask values. By the way, there were two talks from TSN networks here years before. If you can search for Netdev conference TSN talks, you can find. One of them was mine, and there was another a little bit before. And there I explained this QDisk in details. So we have 3 slots here. For priority 1, 10 microsecond, for priority 2, 10 microsecond, for best effort, and at the other traffic class, 20 microsecond. And without the TSN proxy, this looks and we take a look into the listeners, it looks like this. So there are the cycles. So these cycles are looping infinitely. So 10 microsecond, 10 microsecond, 20, 10, 10, 20, 10, 10, 20. It's a loop. And these are the cycles, the cycle number. And here are the time slots. And as you can see, even though the pods are sending with predefined priority, the QDisk see them as priority 0, and they all classified as a best effort traffic, so the listeners cannot, at the listeners, they arrived at the best effort slot, which is not according to their priorities. And if you install the kubectl, just a regular kubectl apply TSM proxy, it can configure anything for you. And then that was the hard part. I mean, for static config, the BPF, testing out the BPF program, it took a week maybe, but packaging this as a reusable CNI plugin, it took months. Or 2 months maybe, or maybe 3 for testing out every single, because we tested it with multiple operating system, Minikube, we tested out with different CNI plugins, primary plugins, and to being compatible with everything, it takes so much time. But at the end, we rendered this into a small container image, which has the eBPF progs, a static compiled BPF tool, since we are relying on that heavily, and we needed the latest version, because only the latest version supported the TC egress program attach at the time of writing. And the CNI plugin is just a bash script. And And we don't use any user space part. Everything what we do can be done with BPF tool. And as you can see, when it's installed, the priorities are the package scheduled according their priority in their correct time slots. These time slots are important. These are the alpha and the omega of TSN networking. There's a network-wide time sync. Everyone define the same time slots, and so the bandwidth are allocated for each traffic class. And if everyone in sync, everyone know when the packet can be scheduled or not. Okay, and the good thing presenting at the last day that there are many experts and you can talk with them and and they tell you a lot of things and the bad thing is your work might be obsoleted by the informations told by experts here. So I briefly mentioned that there's no option to exclude some metadata from the scrubbing process, but that's actually not true for Netkit, since it's like, if someone don't know, Netkit is a VETH alternative, and its transmit callback is a eBPF program, and with ETH tool you can set some flags. For example, you don't want to scrub the priority or the timestamp. You can do that. And of course, there are the proper solution, the packet traits, which I think can be preserved across namespaces, I'm pretty sure. And then you don't need the tracking since those are preserved even if the packet's encapsulated, I guess. And there are other alternatives that's mostly used by the academia nowadays, because there are some research around this topic, and I see it's a popular solution to use Multus. So have multiple CNI networks, but I don't want to talk about this. And the TSN proxy has some limitations. We tested it with many CNI plugins, but we just tried out Cilium. It looked like it works, but it maybe not works if we use enable Netkit instead of VETH, because Cilium also heavily rely on eBPF, so there might be conflicts. We cannot track XDP, cannot track the packets across XDP procession, but it's possible since Peru can do that. We cannot do thorough performance analysis. It looks okay in our tests, but maybe not looks good if there are hundreds of applications, and it can introduce high delay spikes since there's a hash map lookup and it's not free, and the hash map can be different CPU than your packet and stuff like that. And of course, unlike with packet traits, tracking through user space proxy is not possible because they lost the SKB, a new SKB allocated, and you need some kind of tracking across. Okay, and thank you for the attention. I'm a little bit late with the time, so I exceeded my time slot here. And the code is open source, this CNI plugin. If anyone needs such thing, it's possible to try out. Also, I have to mention that this work is partially supported by the European grant Deterministic 6G. It has a page with similar works. And I just want to quickly show there's a paper I wrote it with my colleague, and there are some additional context and references, of course. It's important. Thank you very much for the attention.
Questions? About the bus, you mentioned one product was able to have an ETH tool to select what part of the packet was scrubbed or not. Is it?
You can put it back on that slide.
For Netkit.
So Netkit is what, a series of patch on top of Linux? Or I don't understand this part.
Yeah, no, Netkit is mainline since 6.7.
It's a Netdev.
It's a new network device type, like VETH, but more lightweight. And there's the XMIT callback, which is a BPF program.
Oh, so this part doesn't call the bug scrub, the native function in the
Yes,
kernel.
yes,
Okay,
it doesn't. So you can in the XMIT call, you can encode some redirection or packet mangling entirely, and you don't need allocations.
Understood. Thanks.
Okay, so if that's such a useful feature, why it doesn't exist for VETH?
There are historical reasons. VETH introduced almost 20 years ago, a little bit less, and there might some compatibility issues if we can just...
Well, it's an option, right? The
options from the Netkit options.
Yeah, why can't you just add to that VETH? Since VETH is a much more fit for you.
Yes, maybe just no one.
It defaults to off, and then if someone wants it, they can turn it on.
Yeah, that can be doable.
Yeah, the other question I had for you is, it seems like you're doing a lot of hacks to just make sure you carry the state around. I guess if you turn this feature on, you don't need any of those hacks, right? So you can pass the priority and the SKB marks. Mm-hmm. Another option you could probably look at is an ACT IFE, where you can actually get to put the metadata on the packet. So it has an ether type. So before you send it to the next, you stash your marks, whatever, and then when you receive it on the other side, you run your parser and it puts back your marks.
TC action.
Yes.
It's a mainline TC action.
Yes, it's been there forever. It also works across the wire, so you can go to another machine and it will carry your metadata for you as well.
That's new for me. Thank you.
Yeah.
Maybe I would save lots of time if I can do that.
All right. Thanks. We're running out of time a little bit. Joe, you're next.
In your limitations, you said that your tracking mechanism currently doesn't work for XDP.
Somebody.
But that's not really a problem for your use case, right?
It's not a problem, since most of the CNI plugins, what we tested, doesn't use XDP in their data path. So we can recover the addresses of the packets at the end of the NIC. But if some plugin or proxy or like sidecar uses XDP, we can lose the packet if that's happening. But it's possible to track through XDP as well, since there are conversion from SKB to XDP and back and forth. So you can track that as well. And Peru, I think, can do that. So it's definitely possible. We just don't implement it yet.
Yeah, sorry, we have to cut it out here.
Thank you.
Thanks.